And first of all, I want to thank the organizers for the invitation to this very nice workshop. It's a pleasure to be back in Trieste. So I will talk about sine dilaton gravity, wormholes, finite matrices, and q-holography. And this talk is mainly based on this collection of papers that I published with my collaborators, Thomas Mertens, Andreas Blommaert, Adam Levine, Klaas Parmentier, who's in the audience, and also an upcoming paper that will come out soon with Thomas Mertens and Andreas Belay. So the topic will be this theory of gravity that we introduced and we have studied in trying to establish a correspondence between this theory and the double-scaled SYK model. So just to give some motivation and introduction for why this topic is interesting, at least for us, is that the SYK model is a system with n-Majorana fermions that was dynamics, is governed by the following Hamiltonian. So we have a string of p fermions that are interacting to this Gaussian random couplings. And what's interesting for us in order to find a gravitational dual is that when we go to the thermodynamic limit and at low energies, so with zoom in the IR, then the dynamics of this, the effective dynamics of this theory is described by the so-called Svartian theory, which we have already heard about during this workshop. So it's the theory that emerges on the boundary of JT gravity. So JT gravity is this simple theory, dilaton gravity theory in 2 dimensions, where the dilaton potential is linear in the so-called dilaton field phi. And this theory, in the last few years, has taught us very important lessons about making sense of the gravitational path integral. And but it's not just a toy model in 2 dimensions, because as we have already seen in this workshop, it captures the low energy dynamics of near extremal black holes in 4 dimensions when we zoom close to the horizon. So basically we can learn lessons about the quantum behavior of black holes, because this Svartian theory captures the mode that is governing the dynamics close to the trough. So one natural question that arises is that, can we go beyond this low energy limit? So since we have a full microscopic theory, then we may ask, what is the gravitational dual of the full SYK model? And it turns out that the question to this answer is still not established, at least in my knowledge. But there's a very interesting regime, which is called the double-scaled SYK, where basically one takes a particular double scaling limit. So we take the total number of fermions n to infinity, but also the number of fermions that are interacting here to infinity, in such a way that this ratio here, that we will call log q, is kept finite in the limit. And it turns out that thanks to machinery that is called chord diagram quantization, this theory can be exactly solved in this double-scale regime, and so one can compute the partition function and the correlators exactly, and this is very remarkable. So this is a great opportunity, because we have a theory that goes beyond the low energy regime. So one may ask, okay, can we find the dual to this theory, and this may provide some kind of UV completion of JT gravity, because as we will see soon in the double-scaled regime, basically double-scaled SYK has a bounded spectrum, so the spectrum has a finite support, and also the entropy is finite, so it doesn't grow monotonically with the energy as it happens in ordinary quantum black hole systems. So we can interpret this as some kind of version of UV completeness for the putative gravitational dual we may want to find. And as Klaas already explained in this talk, we argue that the holographic dual to double-scaled SYK is this theory of gravity, which we call the sine dilaton gravity, where basically the dilaton potential is now a sine. You can see that when you expand, when log Q goes to 0, you recover, as the linear term in the Taylor expansion, you recover JT. So this is a deformation of JT gravity. The main idea of this talk and of this collection of papers is that we want to take DSSYK as some kind of source of inspiration, which can teach us some new rules about how quantum gravity should behave. So what are the features that a theory of gravity has to have in order to be UV complete in this sense. And we will see that we will need to insert new ingredients in the gravity description. Let me also mention connected development that has been achieved in the last year that is very much connected with our work. So we can, as Klaas already mentioned, we can perform a field redefinition. So we can introduce the two fields, phi and chi, by considering this conformal factor of the metric rho, and like considering this complex field redefinition with the dilaton. And what happens basically is that the phi r term, using this field redefinition, becomes a kinetic term for these two fields, phi and chi, and the sign potential splits into two exponentials, and these are just the exponential potential of the Liouville theory. So indeed, through this field redefinition, basically we get a double 2D Liouville CFT, but the feature is that we have complex conjugate central charges for these two Liouville CFTs. And they add up to 26. So if one introduces the usual Ghost system, then this can be treated as a string theory. And that's what these people have been doing. So they have named this theory complex Liouville string. And they basically studied string amplitudes in this theory using CFT techniques, so bootstrap techniques. I have to say that our results differ from the results obtained by this group. And despite that, I think this is a very remarkable progress. And we may discuss maybe close to the end, if you are interested, possible interpretation of why the results differ. But I will need this Liouville interpretation many times during the talk. So I will just be very quick in this part because Klaas already described it. So double-scaled SYK can be solved exactly thanks to this machinery of the so-called chord diagrams. So one has some insertions of the Hamiltonians on the thermal circle, which is represented the trace, and then the average over the couplings is basically creating for us these weak contractions, which are represented by these chords. And in order to obtain the partition function, one has to sum over all possible chord diagrams that one can obtain through these weak contractions. And there's a very nice way to perform this sum over chord diagrams, which is by introducing the so-called chord Hilbert space and a transfer matrix. So the rough idea is that we can open up the diagram at one point and define a chord Hilbert space, which is basically given by the number of chords that are running in the diagram at a certain time step. And then for each insertion of the Hamiltonian, we have an insertion of this transfer matrix that can do two things: either increase the number of chords by 1 unit, and there's just one way of doing that, or annihilating a chord. And there are possible ways of doing that. So depending on the position of the chord in the stack, we will get a factor of Q, because each of these diagram is exactly weighted by Q to the power of the number of intersections of the diagram. So that's the important thing. This is the transfer matrix that we will find to be dual to the gravitational Hamiltonian of sine dilaton gravity. So basically, thanks to this machinery, one can compute the partition function in DSSYK as a transition matrix element of this transfer e to the minus beta, this transfer matrix, evaluated between the zero chord state, because of course one has to start with a point with zero chords. And let me also say that one can compute correlators exactly in this theory, thanks to the same formalism. Okay, we have seen in class talks that in the semi-classical approximation of the partition function, the SSYK takes this form, where this piece is the energy that is parameterized as cosine of theta, where theta is an angle. So indeed, as I anticipated before, the spectrum has a finite support. And this would be like the entropy part of the on-shell action that one can tell from here. And the pi theta term is easy to understand because we will soon interpret theta as the area of the black hole horizon. And so the pi theta term is just the Bekenstein-Hawking formula for the entropy. So the entropy of the black hole is proportional to the area of the black hole horizon. So the linear term is just ordinary quantum black holes, but we see that there's a quadratic deviation, okay, that is causing this unusual profile for the entropy. But this is explained in our formalism. In fact, we can perform canonical quantization of sine dilaton gravity. We'll first need to establish a holographic dictionary. So we first consider the semi-classical approximation for the metric correlator in the SSYK. And as class explained, we can consider in sine dilaton gravity the unique geodesic that emerges when we go to the Liouville frame given by one of the two Liouville fields, where basically the saddle of one of this Liouville field is given by an ADS2 black hole. So it's this effective Viry-scaled contour where we have an effective ADS2 background. And indeed, if we compute the length of the Einstein-Rosen bridge in this effective ADS2 black hole, where the temperature is given by this, then the length is given by this expression, and we see that we can match with the DSSYK semi-classical correlator if we match the length in our theory with the number of quarks in the SSYK. So this is basically our dictionary, and we will want to use L as our phase-space variable to quantize the theory. So very briefly, how does the quantization works? Okay, this is a standard in dilaton gravity. One has the two-dimensional phase space in general that is parameterized by the horizon radius theta and the two-sided boundary time t. So t is just the boundary time in this. So this is just a Cauchy slice in my Kruskal extension of the ADS2 black hole. And one considers then the gravitational Hamiltonian of sine dilaton gravity, which is given basically by the ADM energy, that is cosine of theta. And this is just given by the integral, the primitive of the dilaton potential evaluated on the black hole horizon. And then one asks that the symplectic measure on this phase space is left invariant. So I want to perform a canonical transformation in phase space. So I want to go from dt wedge dh, where t is the boundary time that is canonical conjugate to the ADM Hamiltonian. And I want to make a phase space transformation to go to these variables L and P, where L is this length, so the length of the Year-Bree bridge, and P is the canonical conjugate. So I can find the canonical conjugate in such a way that the symplectic measure remains invariant. And then I can basically express T and theta in terms of P and L. And so I can express the gravitational Hamiltonian in terms of the new variables, which are L and P, and the Hamiltonian takes this form. If we use the holographic dictionary between L and N, and we consider like e to the IP and e to the minus IP as the creation and annihilation operators in my transfer matrix that I showed you before, this is exactly the Hamiltonian, the transfer matrix of the SSYK. So at this level, the duality is manifest because we have the same Hamiltonian for the two systems, but there's still a missing ingredient, a very important ingredient, because the number of quarks is of course a discretized value. It takes values 1, 2, 3, while it is very natural to consider a length in the bulk as a continuous variable, of course. But we managed to solve this problem by noticing that the gravitational Hamiltonian here is invariant under periodic shifts of the momentum. So what does it mean? It means that we have an option. We have an option of gauging this symmetry. So as Klaas explained in his talk, we can have the option of not gauging this symmetry and then basically we find some wave functions which give this spectral density, which is consistent with the ordinary linear growth of the entropy of the black hole. But we can also decide to gauge this symmetry, and that considering a periodic variable for the momentum is equivalent to projecting the length to discretized variables, of course, because periodically identify the conjugate means projecting the other variable to discretized values. And in this way, we exactly recover the spectral density of this dSSYK. So gauging sine dilaton gravity is equivalent to dSSYK. And of course, since we are going from a continuous length Hilbert space to a discretized length Hilbert space, there are a lot of states that are projected out of the physical Hilbert space. And this explains why the entropy profile goes down in this way. Okay, so my main goal of the talk is to go beyond dSSYK. So far everything was just on the disk level, but there are some features of the full SYK model that we may want to reproduce with our gravity theory. And the most important one, in my opinion, is the presence of a ramp of the plateau structure in the spectrum form factor of the full SYK. But we know that if we just restrict to the disk, then the length of the wormhole length in sine dilaton gravity can never reach a plateau, for instance. So one may ask, okay, can we find a dual matrix model description of sine dilaton gravity in such a way that we can reproduce these features? Yeah, we know, we are quite confident that the full SYK model is not described by a matrix model. But still, I think this is interesting because we can reproduce features that we may expect in the full SYK. And let me also say that we will find a matrix model that is different from the one of the JT gravity, which is a double-scaled matrix model, as we will see. And so the main goal now is to compute the second most important topology beyond the disk, which is the wormhole. And why this is the most important topology? Because then, using the so-called procedures of disk and cylinders, one can construct the de-brane physics, so de-brane amplitudes, and so like in this way, one can access this non-perturbative physics that we expect to play a role in the formation of the plateau. So this is the goal. So to compute the wormhole in sine dilaton gravity, it's necessary to consider the closed slice quantization of the theory, so the closed channel quantization. So far we considered Cauchy slices that were open with two asymptotic boundaries. Now we go to the closed universe framework, and in particular we want to solve the Wheeler-DeWitt equation. So one knows that in the ADM formalism, if you vary with respect to the elapse function, then you get this Wheeler-DeWitt constraint. And yeah, since time translation is a gauge symmetry in gravity, then you want your physical wave functions to be annihilated by the Wheeler-DeWitt constraint in such a way that these psi's are the gauge invariant wave functions of the theory, so are the real physical states of the theory. Then comes an important step, that is this mini superspace approximation. So in general, like this Wheeler-DeWitt Hamiltonian would involve functional derivatives with respect to the fields, that in this case are the length in sine dilaton and the dilaton. But one can restrict to the so-called mini superspace approximation, where when one just considers the zero modes of these fields, and so basically the functional derivatives are replaced by normal derivatives. And it turns out that in four dimensions, for instance, this is a real approximation. But in 2 dimensions, this is exact. So the mini superspace approximation is exact just because in 2 dimensions, the phase space is 2-dimensional. Then, okay, this is the gravitational, the Wheeler-DeWitt equation associated to sine dilaton gravity. And we immediately notice a feature that is Wheeler-DeWitt Hamiltonian is invariant under periodic shifts of the dilaton. So once again, as it happened in the open channel, there's some kind of redundancy or gauge symmetry that we need to gauge. So we may want to ask that our wave functions are invariant under periodic shifts of the dilaton in order to not to get divergences. And indeed, to like make the similarity clear, we can also note that indeed phi can be regarded as some kind of momentum as it was in the open channel, because indeed what we want to do, we want to find as physical states of the Wheeler-DeWitt Hamiltonian these amplitudes that are called trumpets. So what is the trumpet? A trumpet is basically a space-time geometry where you have an asymptotic boundary, as it was in the disk, but then your space-time ends on a geodesic. And I want my geodesic to have length b when measured with respect to one of the two Liouville frames. And it turns out that this dilaton phi is exactly the canonical conjugate of this geodesic length b. And in order to see it, we can consider like what is the operator that creates a geodesic hole in the bulk. And this is exactly this kind of operator. The way to understand that is that to create a geodesic hole in the bulk, we may also analytically continue basically the length of the hole, b, to complex values, okay? And this would correspond to a defect in the bulk. So if instead of IB here we consider, I don't know, gamma, this would be basically the strength of the defect. How to see that? Because you remember that in the action we have a phi r term. So if we vary with respect to phi, then we are basically creating a conical singularity or a delta functional singularity for the scalar curvature, whose strength is exactly given by the strength of the defect. So indeed, using this analogy, we know that this is we can justify why this is the operator who's creating the geodesic hole in the bulk. And from this form, it's clear, no, it's just a plane wave. So it's clear that phi is indeed the canonical conjugate to B. So indeed, this is a similarity with the open channel where again, we have to gauge the momentum. Yes?
The condition by which you make this quantization condition, the integral operator minus I phi over 2, doesn't seem to be invariant under this gauging that you're doing, right? If phi goes to phi plus 2 pi, it gets a minus sign.
Yes.
Is it an issue or not?
Yes, you're right. I'm wondering if it's just a matter of different conventions that I'm taking or not. But that's an interesting question indeed. Yeah, I think in general we will restrict to positive B's. So maybe that's related. I don't know.
I mean, I guess if you would change something like the orientation or something like that.
Yeah, you can.
It's kind of tricky.
Yes. Yes, you're right. You're right. Okay, we can. Yeah. Yeah. Okay. So we may want to solve this this Wheeler-DeWitt equation, and it turns out it's convenient to go to these Liouville variables that I will call L and L bar. No, this is the length measured with respect to the two Liouville frames. And why is it nice? Because, okay, in the 4-dimensional phase space is now characterized by these two Liouville lengths and the corresponding momentum, which are given by the extrinsic curvature of the Cauchy slices in the Liouville matrix. But now if we go to these Liouville variables, the Wheeler-DeWitt Hamiltonians basically factorizes. So we have a part that just depends on L and K and a part that depends on L bar and K bar. So what does it mean? It means that the wave function factorizes, so I can just use separation of variables and say that this part is equal to a constant and this part is equal to the same constant, right? And I will call this constant B. And yeah, when I promote K to be an operator, so it will become E d over dl because it's the conjugate to L, right? Then this becomes the equation that I need to solve. And the wave functions are given by Bessel functions. In particular, I have a basis with the Bessel J's function and the Bessel Y functions. But it turns out that I need to construct this particular combination, as we will see soon, to construct a wave function that has the nice property that I want in the asymptotic limits, as we will see soon. And yeah. So let me also recall that this is a finite cutoff trumpet because so far we haven't imposed any boundary condition, for instance, on the dilaton. So this is a trumpet, a finite cutoff so far. And let me also say that the wave function factorizes in this way. So this depends on L, this depends on L bar. Okay, so these are the physical states because they solve the Wheeler-DeWitt equation. Now I want to consider the position of the holographic screen, that is this weird location that Klaus talked about. I will come back to that later more. But in general, when I go to this position of the holographic screen, then this quantity is finite and is basically the length of the boundary. And if we stripped off a phase with an holographic counter term, that particular combination of Bessel functions just reduces to this Bessel I B of beta. But so far, B is just a parameter that is labeling my classical solutions because it's something that I use to solve the equation through separation of variables. So I want to give a physical interpretation. I want to be given by the length of the geodesic. So how to see that? Because, so why this identification? Because if you consider just the first part of the Wheeler-DeWitt equation that we used to solve with separation of variables, we see that basically if we consider a geodesic, so with the extrinsic curvature that is vanishing, right, then this means that L is equal to B on this particular slice. So if we imagine to start with a slice here, then L is indeed given by B, right? And then the Wheeler-DeWitt equation is telling me how this state evolves as I change the extrinsic curvature from a geodesic to another type of curve. But so this allows me to identify this P with the length of the neck of the trumpet here. And I can also do a semi-classical computation if I will have time later, where I can also make this identification clear in another way. But then what's the most important step? So what is the effect of the gauging on the spectrum? So in order to see that, in order to appreciate that, we can take this particular limit of the wave functions, the L to 0 limit, and it turns out that that particular combination that we constructed exactly reduces to a plane wave. And this is exactly what we wanted, right? Because this is basically a manifestation of the state operator correspondence. Because if you imagine to perform a tiny path integral with this defect operator insertion, so what happens is that the topological piece of the action will provide me with e to the 2 pi phi, right? Because we are on this topology. So it will cancel this term, and I will end up just with a plane wave. So it makes sense that there's just an operator, state operator correspondence, so the operator is exactly creating the state that I want in this limit. So in the limit where we have a tiny path integral around the point where my operator is inserted. And then this is a plane wave, so it's clear what happens. No, if I gauge the symmetry, then B has to be discretized, as it happened in the open channel. So B has to take integer values. And okay, let me also say something that will be useful later, because once I have these trumpets, I will want to construct the cylinder amplitude, so the wormhole. So I would want to glue two trumpets together along their common geodesic in the middle. But in order to do that, I need to know what's the identity operator in this Hilbert space. So to do that, I need to compute the inner product between these physical states. And it turns out there's a natural Klein-Gordon inner product, which is basically inferred from the Wheeler-DeWitt equation, and it takes this form. And it's useful to compute it in this limit because it's very simple. And indeed, you get this orthogonality relation between the states, which will be useful later, as we will see. Okay. I guess we have some time to derive the same amplitude in another way. So far we obtained the trumpet using this Wheeler-DeWitt closed channel quantization, but there's actually a way to obtain the same amplitude using an open channel formalism, right? And this is using the so-called end-of-the-world branes in Sine dilaton gravity. So it's a treatment that is quite similar to the one in JT gravity. So first of all, what's an end-of-the-world brane? It's like a different type of boundary conditions. So usually One is interested in asymptotic boundary condition, where one fixes Dirichlet boundary conditions on the asymptotic value of the metric and of the dilaton, for instance in JT. But there is also a different set of boundary conditions, so I can make my space-time end on the trajectory of a boundary particle, of a boundary brane, right? By introducing these boundary terms which are integrated on the word line of the brane trajectory. And in particular, the most general brane that I can construct is by coupling the two Liouville fields, basically, with the two cosmological constants for the brane, which I will call mu and mu bar. And if I solve the boundary conditions for the theory, so I just impose that I have a well-defined variational principle, then this implies that basically these constants mu and mu bar are determining what is the acceleration of the brane in these two Liouville frames, right? Because I can regard K, the synthettic curvature, as the acceleration of the brane. And let me also tell you that through the Will-DeWitt equation, one can prove that actually in the space of all branes, not all of them are inequivalent. Like if I pick two branes whose values of mu and mu bar share the same value, the same value of this combination, right? Then these two branes are gauge equivalent one to the other. And this makes sense if you think about the Will-DeWitt equation, because the Will-DeWitt equation was coupling basically K and K bar, no? So, and it will turn out that this gauge invariant quantity is once again given by the dilaton evaluated on the black hole horizon. So very quickly, the computation is highly technical. I just want to highlight the main steps. So I want to use the so-called semi-open channel quantization. So what's the framework now? Now I have a boundary brane here, parameterized by mu and mu bar. And I want to compute the length of this slice here that is ending on one side on the asymptotic boundary and on the other side on the constant accelerating brane. This is a very non-trivial computation to compute this length in a effective ADS2 background, but this is the form of the result as a function of mu and mu bar. And then I perform the usual gape once again. So I just require my symplectic form to be invariant, but now I want to go to this new phase space variables where L semi is this length of the semi-open channel here, and P semi is the dual momentum. Then once again, as we did in the full open channel, then I can invert this expression and find the Hamiltonian of side dilaton gravity in the presence of a brane. That I will denote with H mu mu bar, and it takes this form. And it turns out that after I gauge once again this symmetry of the shift of the momentum, then the wave functions are discretized once again. And while in the full open channel, the solutions were given by these Q-hermite polynomials, as Klaas was explaining, now they are given by these Al-Salam-Chiara polynomials. Okay, these are just a different type of Q polynomial. But it turns out that then, if I want to use this formalism to compute a trumpet, what do I have to do? I have to construct this cylinder amplitude, right? So I have to trace over this Hilbert space because I want the trajectory of the brane to be cyclic, if you want, to be periodically identified, right? So on one side, on the asymptotic boundary, this semi-open channel will draw a circle of length beta, and here, basically, we are drawing a circle on the brane trajectory, and then I want to perform an inverse Laplace transform. And it turns out that I have to, like my exponential weight is exactly given by this combination, which involves this gauge invariant quantity phi h. And this computation is quite involved. You have to compute the trace with these wave functions and then compute this inverse Laplace transform. I just skip all the details, and the reassuring fact is that we obtain once again the same amplitude. So this is nice because we obtain the same amplitude in two different channels, with the open channel and with the closed channel. So the two results are consistent. And also, if one is still skeptical, one can compute, for instance, also semi-classically this amplitude, this trace over e to the minus beta, the brane Hamiltonian, by constructing a path integral where I just compute the Lejeune transform of the brane Hamiltonian. And I want to find, since I want to compute the trace, I would like to find periodic solutions to the equations of motion. And in particular, I will look for time-independent ones because I want to construct this U1 symmetric cylinder. And if I plug the solutions back into the action, then I find this particular Hamiltonian, which, as you can see, depends on this particular gauge invariant combination that I was mentioning before. So it's reassuring that we get the same gauge invariant combination that we obtained before. And then I have to basically do the, so I have to do the inverse Laplace transform of this object, and this is indeed the integral representation of the Bessel function. So again, also semi-classically, we find a match. Okay, so now that we have the trumpet and we have the identity operator, which is given by this this thing here, where I have to insert the measure that I computed with the inner product. So I can glue two trumpets together. So I have a trumpet here with asymptotic length B1 and a trumpet here with asymptotic length B2. I insert an identity operator in the middle, and I need to evaluate this sum. And yeah, one can do that in closed form and perform an inverse Laplace transform with respect to the two boundary lengths to compute the spectral density, the spectral correlation density. And it takes this form. And it turns out that this is the universal leading order spectral density in finite cut matrix integrals. So not in double scale matrix integral where the support of the spectral density is infinite, like in JT gravity, the spectral density is sin square root of E, right? So one has to send the number of eigenvalues to infinity while at the same time zooming on the spectral edge of the spectrum to have a double scaling matrix model. In this case, we have a finite cut. So the eigenvalues are just on a finite portion of the real line. And so also the dimension of the matrix is still large if I want to do some kind of topological expansion, but it's not infinite because I don't need to double scale like on the spectral edge. So since we matched both the disk and the wormhole, right? This result suggests that our theory, so sine dilaton gravity, is the path integral formulation of this ETH matrix model that was introduced by these people, remarkably. And indeed, this is the matrix integral definition of Q-deformed JT gravity. So what these people did is basically construct what would be a matrix model for the SSYK by just tuning the matrix potential in such a way to reproduce as the leading order at large n the spectral density of the SSYK, and we find that we obtain both the disk and the cylinder in our theory. But of course, you may of course ask, okay, but a full identification like it happened in JT gravity between our theory and this matrix model would require to compute the path integral of sine dilaton gravity on some higher genus topologies, like for instance the disk at genus 1, the disk at genus 2, I don't know, and then to match at least some topologies to make the claim. But okay, this is something that we are still working on, so it's still an open question. But what we have done is a consistency check, which I think is promising. So there's a particular limit which is called tau scaling limit, which was used in the case of JT gravity. So one can consider the spectrum form factor of a theory, right? And consider very large times where basically the time scales with the dimension of the matrix. And so what we did, we employed the topological expansion of this matrix model. So we computed, for instance, the spectrum form factor at genus 1 or at genus 2, etc. And then we consider this particular double scaling limit, right? And what we get is that we obtain these perturbative terms in the expansion at large tau, in tau, okay? And these perturbative coefficients here are exactly consistent with the D-brane non-perturbative physics, meaning that once I have the disk and the cylinder, I can use this method of the disk and cylinder approximation to construct a D-brane amplitude. And this is basically giving me the spectral correlation density of the sine kernel, which is giving me, if you want, the repulsion of the energy eigenvalues as they get closer to each other. And this would be the prediction, these coefficients would be the prediction of this sine kernel, which becomes exact in this tau scaling limit. And indeed, we find a match. So this is not, of course, a proof of the duality, but it's still nice that we can construct first the brane effects and see that these are consistent with the topological expansion. You may ask, what is this? Yeah, besides these perturbative terms, we find also these non-perturbative terms that scale as 1 over n. But we also managed to explain these terms because they are associated to one eigenvalue instanton terms in the matrix model. And indeed, as Klaas explained, this matrix model can be seen as a deformation of the Gaussian matrix model, where this one eigenvalue instantons are present as well. So, okay. Yeah, we found the solutions of the Wheeler-DeWitt equation as our physical states in our theory, but then we may ask, okay, can we decompose the disk amplitude? So the disk should be decomposable on this basis that we found, right? And in general, what happens is the most famous boundary condition is the so-called no boundary initial state. So what one has to do is to take the trumpet here and glue it with an Euclidean preparation region, right? In such a way that your wave function has no boundary, so it's pretty smooth. So the prescription is basically to glue here your amplitude with the amplitude of an hemisphere in the Euclidean preparation region, and to tune exactly the neck of the trumpet to be related to the radius of the hemisphere, which is giving us the Euclidean preparation, right? So another way to say that is that I can decompose my no boundary wave function this way by integrating over all possible lengths of the trumpet here. But then this psi no boundary, right, has to be a delta function. As I was saying, you have to make this B match with the radius of the hemisphere in the Euclidean preparation. Another way to see that, if we consider the operator that was creating my geodesic hole in the bulk, you see very clearly here that when B has to be equal to 2 pi I, in such a way that this becomes the identity operator. So it's just saying there's nothing there. So we have a smooth disk. But, so it's basically asking that there's an absence of a conical defect in the bulk. But the point is that, okay, this state is non-normalizable, of course. But it's not physical in sine dilaton gravity, because in sine dilaton gravity, we saw that B has to take discretized values. So this value 2 pi I does not belong to the physical spectrum of the theory. So this is saying that the naive no boundary state does not exist in sine dilaton gravity. So what is replacing that? Something else. And we can compute what this something else is. So what is this different wave function that is weighting the trumpets to obtain the disk? Because indeed on the left-hand side, we have the disk that we computed in the open channel. So we know the result. And so basically we know the form of the trumpets, and now we can ask what is this psi B, where of course now the integral over B has been replaced by a sum, because our physical Hilbert space runs over discretized geodesic lengths. And this psi disk takes this particular form in our theory, and it turns out, if you plot it, that this is a Gaussian, okay, that is exactly centered around the same value where the delta function was located. So it's like saying that in some kind of UV complete models of quantum gravity, if we can call sine dilaton like that, or in general periodic dilaton gravity, like the duality with this TSSVK is in some sense telling us that we have to pick a different set of initial boundary conditions, which smear the usual no boundary state, which is a delta function and is non-normalizable, into a Gaussian, which is now normalizable. So we can take this as a lesson for how the initial conditions have to be in this theory, since this theory can be regarded as a UV complete theory in this sense. Okay, now it comes the very last part of the talk, where I want to explain a bit better this position of the holographic screen that Klaas explained in his talk. So in sine dilaton gravity, we have to consider this effective contour along which one of the two Liouville fields is real, and its saddle is just given by an ADS2 black hole. But if we trade this contour back in the original variables, this corresponds to a complex contour in the phi r plane. But okay, what we observe is that the Ricci scalar blows up as we approach the holographic screen here. So it seems like there's some kind of holographic singularity in our theory. So we want to understand better what this singularity is, and to characterize better what happens close to the holographic screen in our theory. So one way to understand that is to characterize the algebra, the induced algebra on the boundary. So we computed before the Hamiltonian of sine dilaton gravity, which takes this form, right? And by performing a Legendre transform, this becomes a path integral description of sine dilaton gravity. So this path integral is giving me the boundary dynamics of sine dilaton gravity. And this path integral is called the q-Schwarzschild path integral. Why? Because it's a deformation of the ordinary Schwarzschild path integral that governs the boundary dynamics of JT gravity. And in particular, the way this q-Schwarzschild path integral was first derived by my collaborators was studying group theory, right? Because in analogy with JT gravity, we know that the Schwarzschild theory, right, can also be regarded in the first order formulation as a particle on SL2R, right? But then this path integral then emerges as this description of a particle on a quantum deformation of the group, where one has to impose some auxiliary boundary conditions to get rid of some of these fields, right? So this path integral is part of a more general theory with 6 fields, which is indeed this particle on SUQ1, 1. But it turns out that if one computes the classical conserved currents of this theory, you can show that they obey like these Poisson brackets, right? Where you see this is a deformation of SL2R, because if you send log Q to 0, then here you have E, the Poisson bracket between E and F equal to H, and this is just the Poisson bracket which upon quantization give the algebra relations of SL2R. So what we want to do, we want to study the 2-point function, right? And using this symmetry to constrain its form. So in a CFT, what you can do is you can constrain the form of the 2-point function by using the so-called global conformal word identities. And since SL2R is just the global part of the full Virasoro algebra, then you can require that your 2-point function is invariant under the action of these three generators, and you basically find this the standard conformal answer. So one may ask, okay, can we do the same thing with the Q-deformed setup? So can we ask the 2-point function of these two operators to be invariant under the global part of the Q-conformal group, which is exactly given by these generators? Yes, you can. And you need to construct a representation, right, of these generators. So see how they act on these operators, right? And so you have 3 Q-deformed word identities, and you can solve them. And it turns out that the solution of these 3 word identities takes this form, where tau here is the difference between the position of the 2 operators, the insertion of the 2 operators. And these are these special functions are the double sign functions, right? So you can show that this satisfies simultaneously all the 3 Q-deformed word identities. So the question is, can we find this result from a gravity calculation? Can we embed this result in sine dilaton gravity in some way, right? Because we expect this result to emerge in some kind of limit as we approach the asymptotic boundary. So we have not managed so far to obtain this result directly in sine dilaton gravity, but there's a broader theory to sine dilaton gravity, which is Sine dilaton gravity, where basically you have to analytically continue this value log Q, right? So instead of having Q from 0 to 1, as it was in the SSYK, now we analytically continue to Q on the unit circle, right? And by doing that, basically the sign becomes a singe, right? And this theory is called Liouville gravity, or is known as Liouville gravity in the literature. And if we go back, if we again perform the filter definition that I showed you at the beginning, one can go to a string formulation of this theory, where instead of having two Liouville CFTs with complex conjugate central charges, you have two Liouville CFTs, so a time-like Liouville and a space-like Liouville, but now with real central charges. And again, you can add the ghost and form a string theory, right? But this is the gravity formulation of this string theory, basically. And one can study the classical solutions of this theory. So the main point is that, okay, we still don't know how to get that result in sine dilaton gravity, but we may want to understand something in this very closely related theory, right? And we will see that it shares more or less the same features. How to see that? Because if we consider the classical solutions of the theory, right, they take this form. And if we expand in the deep interior, so when the radial coordinate is small, then this reduces exactly to the ADS2 black hole of JT gravity, so the black hole patch of ADS2. So like deep in the interior of our theory here, we have JT in the IR, right? But then, if you consider the scalar curvature in this theory, right, we see that like close to the boundary, we have again a singularity, you know, when R goes to infinity, that the scalar curvature blows up. So that's why we can say that what we can learn in this theory, we can also, in some sense, learn something about sine dilaton gravity, because also there, the Ricci scalar was blowing up close to the boundary. And it turns out that as we go close to the boundary, so we increase our energy, so we go to the UV region, we are basically deforming away from JT, right? And this can be seen, for instance, by computing the saddle point or the partition function, and you can see that at small energies, you just recover the relation between energy and temperature of JT gravity, but then as you increase the energy, then this relation is deformed away, right? So from this, we can say that the boundary is in some sense located the boundary can be found in the UV. So at large energies, we are basically going closer and closer to the boundary. So what can we do? Okay, we can take the 2-point function, the bulk 2-point function in Liouville gravity, which take this form, right, with these functions, and then we want to perform an approximation, right? So our approximation is that, okay, we want to do this change of variables, so this is given by a double integral in terms of this variable S1 and S2. So I want to do an approximation where basically I consider a large background energy, so a large black hole energy E, because I want to go close to the boundary, so in the UV. And then this S1, S2, okay, which label my energy parameters, have to be very close to each other. So I want to basically expand a leading order in omega, which is the energy difference, right? And the energy difference has to be small compared to the average energy, because I want to inject into the bulk a small probe, which is not altering my geometry. So it has to be also light. The conformal dimension of the operator has to be light in such a way that it doesn't deform the saddle point on my geometry, because I want the probe to be just a probe and not to backreact on the geometry, in such a way that basically the saddle of the integral over E, once I do the change of variables, is again given by the standard relation between energy and temperature of Liouville gravity. So this is like going from the canonical ensemble to the microcanonical ensemble. And then how to deal with the integral over omega, right? We can imagine that we can extend the range from minus infinity to plus infinity, because m is always larger than omega. And there's this very nice formula by Ramanujan, where basically you can do the Fourier transform of the object that you find here by expanding, and you exactly land on the result given by solving the Q-conformal word identities. So this is nice, because in some sense we see that this regime is there in our theory. But there are some caveats. So first of all, some comments. So it seems like singe dilaton gravity and maybe also sine dilaton gravity, because we may hope to find a similar formula involving Q-Pocameral symbols, for instance, but we have not managed yet. So it can be seen as some kind of realization of this quantum holography. As far as we know, this is the first instance where there's a proposal where this quantum holography emerges in a clear way, I think. And so this is also in line with the logical expectations, because this quantum geometry is basically saying that there's a non-commutative space-time there when we go close to the boundary, right? And this is in line with the expectation, right? That there should be some quantumness or some non-commutative space-time when to naively cure the naive classical singularity that we had there. But there's a caveat, because when we set delta to be an integer, right, we can simplify that expression with the double sine function into this much simpler formula. So first thing to notice, okay, we have a product of these signs, okay, with a shifted argument. But if you send b to 0, which is basically going to JT gravity, then you have a sine to the power of 2 delta, which is exactly the thermal conformal answer in JT gravity. So indeed, this goes to the correct limit. But as we see here, right, this expression should develop some poles, okay? So the JT gravity expression just blows up at tau equal to 0, at tau equal to beta, right? But this expression has more poles, right? So because of these shifts in the argument of the sign, this expression should develop some poles here in between. But this is a numerical evaluation of the full result without taking any approximation. And we see that there are no poles. So the solution is continuous, and it's also quite similar to the semi-classical result that you would obtain by sending b to 0. So what's the conclusion that we are still working on that, but we are basically observing that unlike in JT gravity, where this probe regime, so sending a small probe with a large black hole energy, would correspond to a semi-classical regime, right? In this case, like the semi-classical regime, so sending b to 0, would make us land again on the conformal answer. So this is not like this probe regime in sine dilaton gravity is not a semi-classical regime. It's a highly quantum regime. So that's why we don't see this pose appearing. So we can, in some sense, think of this result as some kind of extrapolation of the 2-point function as we go close to the boundary. So there's like a portion of the Hilbert space at high energies where this quantum geometry appears, and the probe can feel this quantum geometry. But as we go deep into the bulk, then these singularities are in some sense not there. So the full quantum gravitational description is not given just by this quantum geometry. It's something that appears only asymptotically. This is the interpretation that we are giving, but we are still thinking about that. There's been a proposal, for instance, by Almeri and Popov, that indeed this non-commutative geometry, what they called quantum disk, is the dual to the full double-scaled SYK. But in some sense, this computation shows that no, it cannot be. So we indeed find this regime, but just asymptotically. It's not the full regime. Yeah. Okay. Do I have still 1 minute or?
1 minute, yes.
Allora, okay, then very quickly, I want to say just one thing, since there have been some talks about the near extremal black holes, and so the audience is interested about that. There's something that we have been thinking about very recently with my collaborators in Ghent, which is the fact that if you dimensionally reduce the 4-dimensional Einstein plus Maxwell plus cosmological constant, right? With this ansatz for the metric, which is the same ansatz that Chiara Toldo was showing in her talk. And then we fine-tune the parameters to be the ultra-cold case that, as Chiara told, is just here in the sharp fin, right? This peculiar point here. Then the effective 2-dimensional theory that we find takes this form, right? So it's just the R phi plus a very small fluctuation that is quadratic in the dilaton, right? And as Klaas showed in his talk, we can actually we know how to quantize this theory, because this theory is exactly obtained by expanding the Sine dilaton potential around the maximum at pi over 2. And as he explained, this is a regularization of flat space JT. And you can see it here, no? Because if you vary with respect to the dilaton, then you have almost r equal to 0, right? But this is a small quadratic fluctuation that is creating a cosmological horizon very far away. So this is like regulating your flat space JT. So an hope that we would have, okay, since JT gravity can be used to extrapolate lessons about this higher dimensional black holes, okay, maybe can we embed DSSYK in this more this four-dimensional black hole and extract some lessons, since we know how to quantize this theory in this limit. So this is still an open question, but we hope to investigate more on that. So these are just the conclusions, but I guess I can skip them. I thank you very much for the attention.
Thank you. Any questions? So in double scale SVK,
Yes.
you can try to compute in the actual model the leading connected contribution. You have two boundaries.
Mm-hmm.
And you find that there is something that comes before at intermediate times. You find that there's something that contributes more than the connected geometry. So the connected geometry is suppressed exponentially in n, but you also have contributions that scale like 1 over n to some power.
In the full SVK, you mean on?
In double scale.
Okay.
Something like 1 over n to the power of p.
Okay.
So n to the square root n.
Okay.
And do you see anything like that on the Sine dilaton model?
No, but yeah, I didn't know about that actually. So
it's related to the fact that at the end, all of these SVK models have way less parameters than a dilaton matrix. Right? You choose a bunch of couplings, but the number of couplings is n to the q, while the number of random couplings in a random matrix is exponentially n. And so you see some intermediate behavior that is more important than the rank at this time scale.
I see. No, but we should think about that. Thanks.
Any other questions? If not, let's text because
Thanks.
So we need some